Okay, so hello, welcome to the easy part of the course. So now you can relax. This is going to be quite easier with respect to the previous part of this course. So this presentation, this part will be focused on the C++11 smart pointers. So I will start with the old style raw pointer. So I'm pretty sure that everyone here knows everything about this old style raw pointer. You can have basically two different type of. Okay, as I was saying, you have more or less two different type of, let's say, of allocation for your raw pointer. You can have a pointer that points to a variable which is located dynamically allocated on the heap, which is for this first case when you use the new operator to create a new variable. In this kind, it is a t type on the heap, and then you have a pointer that points to this new variable. And in another case, you can have, for example, a pointer of the same type, but in this case, it's pointing to a variable, to a local variable, a variable on the stack. The main difference here is that, of course, in the first case, you have to remember at the end, let's say, of the usage of your pointer to call the delete operation, otherwise you will have a memory leak. Another difference between pointers can be when you have a pointer to a single object, like in this case, or a pointer to an array. In both cases, you are working with a dynamically allocated variable, but in the first case, it's just a single object. In the other one, is instead you are dealing with an array. So this is just to say that, I mean, these are the typical usage of the raw pointer, and if you're doing things like this in the internal part of your code, if you're working on the development of the library, and this kind of stuff is in the internal component of your code, everything is fine. I mean, as far as you remember to delete the allocated resources, you don't have any problem. Some problems can arise if you start to use this kind of pointer, the raw pointer, in the interface of your library. If you're thinking about providing an API for other user that will use it for development of their code, the problem is that sometimes can be, let's say, dangerous to provide this kind of pointer in the interface of that kind of function. So let's take, for example, this function. This is more or less a random function from the GSL. It's something like a function that allocates a kind of a non-linear solver, whatever, but it's not important. The point here is that the documentation of the GSL is quite clear, so that you can perfectly understand what's going on here with this function that is returning a raw pointer. The problem is that is when the documentation of this library is not so clear. Maybe you don't have let's say, a clear documentation of what is happening with this pointer, because here is not clear, for example, for the declaration of the pointer, if this pointer is pointing to a single object or a single array, to a single object or an array of objects. So you don't have this information if you just look to the declaration of the pointer, because it is exactly the same expression. Another problem is that, for example, you don't know, in principle, if you are responsible for the destruction, for the release of the memory that have been allocated during the call to this function or not. Another possible problem is that, assuming that you know that you are responsible for the release of this memory, you don't know if you have to follow a custom delete procedure provided by the library itself, which is the case of the GSL library. You have to call some kind of multi-fit release function or something like that. Or maybe you can just call the standard delete operation on your pointer. And there are many other possible issues here. For example, if you know that you have to call delete, the problem is that you don't know if this is just a pointer, a single object, or a pointer to an array. So you don't know if you have to call delete or delete with the square bracket to avoid memory leak. And if you have to delete the resource, if you have the responsibility for this memory release, the problem is also that you have to consider all the possible execution path of your code. Not only, let's say, the straight one, but also all the cases when you can have exception and stuff like that. Because otherwise, also in that case, you will have the memory leak. Another big issue is that with this raw pointer, you don't know if the pointer at some point is a valid pointer or it is dangling. Because maybe in some other point of your code, the resource originally pointed by your pointer has been released, so that now you have a pointer that is basically pointing to a memory location that is no longer there. This is to say that there are some problems basically in using the raw pointer, and the basic idea of a smart pointer in C++11 is just to remove all these possible problems while providing an interface that is almost completely the same with respect to the one of the raw pointer themselves. So, what are these C++ smart pointer? Basically, they are objects that, as I told you, behave more or less like the standard raw pointer, but that remove the responsibility to the user for the management of the lifetime of the pointed resource, which is in this case the allocated memory, basically. You can, if you want a kind of mental model also for this case, you can imagine the smart pointer as a kind of wrapper around the raw pointer that provides a set of additional facilities that basically allows a smart management of the allocated memory. And as I told you, the interface is such that basically they can use it in your code in the same way of the standard raw pointer. So that basically if you want to move, if you want, let's say, update your code in order to use this new raw pointer, basically you don't have to change a lot of code because the interface for the standard operation with the raw pointer is almost the same of the smart pointer one. There are three different types of smart pointers. We have two pointers types, which are the shared pointer and the weak pointer that implements the shared ownership semantics, which means then we will see more details what we mean with that, but basically it means that you can have more than one instance of shared pointer or weak pointer that are pointing to the same memory resource, to the same memory location. And then we have another kind of a smart pointer, which is the unique pointer that instead implements the unique ownership semantics, which means that basically you can have only one instance of unique pointer pointing to a given memory allocation. There is also another type, a last type of smart pointer, which is the auto pointer, but this type is just a deprecated leftover from the old standard, and it is more or less, it is equivalent to unique pointer. So don't use the auto pointer since we have the unique pointer, which is basically the same thing, but but this is part of the last standard. Okay, so before going on with the details of this smart pointer, I just want to remind you something about the RAll idiom, because the smart pointers are an example, a good example of application of this pattern, basically. So, as Mauro already told you, the meaning of RAll is resource acquisition, is initialization. And another way to define this, which is maybe also a bit more clear, is scope-bound resource management. But okay, besides the definition, the point is that the basic idea of this idiom, of this pattern, is just to provide an object representing a given resource and implemented in such a way that the destructor of this object could release also the managed resource. So the idea is that basically if you use, instead of using something like, instead of directly using the resource itself, that would be in the case of the raw pointer accessing, using the raw pointer itself and directly accessing the memory, the idea of the RAll idiom is to provide you an object that represents the same resource, which is in this case the memory allocation, but that remove from the user to the user the responsibility of basically of releasing the allocated resource, so that you're no longer responsible for the management of the resource that you are using, because everything will be controlled by the object that is implemented in the RAll idiom. We have two kinds of, let's say, of ownership of the resource that we are using. As I told you, we can have an exclusive ownership of the resource, which is the case of the unique pointer, where you can just have one instance of unique pointer that is somehow controlling the user resource. And you can have also another type of ownership, which is the shared ownership, which is the case of the shared pointer and of the weak pointer. And in this case, you can have more than one instance of this kind of object that are controlling the same resource, the same memory location in this case. Memory location is not the only kind of resource that is controlled by RAll idiom. In the STL in particular, you can have other type of object, and we maybe, if we have the time tomorrow, I think that we will see also this kind of stuff, but in this case, the resource which is controlled by this object that are implementing the same idiom is not the memory, but instead is the mutex, which is, let's say, something that controls the threads of execution in multi-threading. And the other cases of application of the RAll idiom in the STL is represented by the container. The vector, the standard vector, is an application of this idiom. Again, in this case, you are controlling as a resource a memory location, but you are not destroying, let's say. You are not doing that manually. You can create a local vector, with the local I mean a local variable as a vector, and when you finish to use it, when it goes out of scope, the resource which is used by the vector itself, which is a dynamically allocated memory location, is automatically destroyed by the destructor of the vector itself. So this is just to remind you about the RAll idiom, which is very important also in the other cases. Okay, so let's start with a small example of application of this shared ownership pointer. Let's have a quick look to this main function. So here I'm doing some very basic stuff with the smart pointer. The most important line, I guess, that it is the first one, where here we are creating our first example of a shared pointer. So as you can see, I forgot to tell something about the definition, but okay, all these smart pointers are class templates. They have just one parameter, and the parameter is represent the type the pointer is pointing to. It is basically like the type of the raw pointer. Okay, in this case, we have a shared pointer that is pointing to a double type, and so you have to specify the type double as template parameter. Okay, quite easy. So this is the first call to a constructor to the constructor of the shared pointer, and by definition, you have to pass to this constructor a raw pointer to the same type specified by the template parameter. So in this call, you are creating you are dynamically allocating one double. I know that is not a good example, but in any case, you are creating a single double with value 23. You are dynamically allocating this variable, and the pointer that is returned by this call is provided to the constructor of the shared pointer object. So this is the way how we create a shared pointer. Then, as I told you, the smart pointer are defined, the interface of the smart pointer is defined such that you can use them more or less as you do with the raw pointer. So, for example, I can check the validity, I can get the value pointed by the shared pointer, like you will do with the standard raw pointer, just by using the dereferencing operator. You can create a new shared pointer using the copy constructor, for example, and this is the first case where we have two shared pointers that at this point are pointing to the same memory location. We can create a shared pointer using the default constructor that in this case, like for the raw pointer, will create a shared pointer that is basically a null pointer, so a not valid pointer. Here we can assign one shared pointer to another one. So basically this pointer that was originally a null pointer now is assigned to the same memory resource of SP1. So that at this point we have three shared pointers that are pointing to the same memory resource. We can use the move constructor of the shared pointer. So basically, in this case, we are creating a new shared pointer that is pointing to the same memory, to the same original memory location. But after this point, you will have only three smart pointers that are pointing to the same resource, because when you use the move semantics on the shared pointer, basically you are somehow detaching this initial shared pointer from his memory location. Other things that you can do, which are similar to the raw pointer case, is just to set the shared pointer to null pointer, for example, and you can also check the validity of the shared pointer, like in this if block, basically. And okay, in the last line, basically, I'm showing you how to create another kind of shared pointer, which is the weak pointer with the same type, using the constructor that takes in input the shared pointer type. So this is the basic interface. It was just to show you how to create the shared pointer, how to move them, and so on. The good news here is that after the end of this scope, so at the end of the execution of my main function, I don't have any memory leak, even if I'm dynamically allocating a memory location here. And this is basically the reason why we introduce a shared pointer, of course. So the question here is how can this stuff work, basically? What is let's say, more or less the implementation? We will not see, of course, the details of the implementation, but it is important to have an idea of how this kind of stuff works. So basically, the idea is that a shared pointer and weak pointer are the so-called reference counted pointers. It means that basically, when you create a shared pointer, which is a weak pointer or more smart, or sorry, when you create a smart pointer, which can be a shared or a weak pointer, in this case, you're not only allocating a memory resource on the heap, but you're also creating another object which contains the information about the current status of that memory location. Basically, it means that we have a situation like this one. When you create a shared pointer, you're not only creating this one which represents the memory allocation, but you are also creating another object, which is the so-called resource manager, which contains some information about the status of this pointed resource. And in particular, it contains two counters, which, let's say, take into account the number of smart pointer, of shared pointer, and of weak pointer that are pointing to the same memory location. So in this case, we have just one shared pointer. We have created this shared pointer, which automatically creates this memory location, and also this resource manager. And the status of this object at this point is that is represented by this condition for the internal data members, which means that we have just one shared pointer and 0 weak pointer. Another data member of this object is represented by a raw pointer, which points to the original memory location. So basically, this is a mental model. Of course, it's not the real implementation, but the real implementation is, similar. There are some differences, but more or less it is the same. And so you have always to remember that we have this kind of conditional. Both these objects are dynamically allocated, so that when you create a shared pointer, you are doing two dynamic allocations instead of just one. One for the resource manager and the other one for the managed resource. This one is basically the one that you create when you call the new, when you do this call, basically you are creating the pointed resource. The creation instead of the resource manager is, of course, managed by the constructor of the shared pointer. So how this is used by the smart pointers to automatically control the lifetime of the managed resource. Basically, the idea is that when the number of shared pointer and the number of weak pointers in general is different from 0, we have the memory resource is always alive. When the number of shared pointer goes to 0, also the managed resource is deleted. But the resource manager is still alive. The resource manager is deleted only when the number of weak pointer also goes to 0. But this is all automatically managed by the smart pointer themselves, so that you don't have to worry for the destruction of the managed resource or the destruction of the resource manager. So just to give you an idea of how things work, let's make a small example that more or less corresponds to our initial main case. We start with a single shared pointer. As I told you, this corresponds to the creation of the resource manager and to the allocation of the managed resource. So that in this case, we have that the number of shared pointer is 1. We don't have any weak pointer, so this variable is 0. And then we have the raw pointer that points to the managed resource. If we follow our initial example and start to create other shared, yes, this is right, okay. If we start to create other shared pointers that are all pointing to the same resource, because we are using, for example, the copy constructor or the assignment operator, we are just increasing the number of the shared pointer that are pointing to the same memory resource, which is unchanged, of course. And also, if we start to create a weak pointer, as in our main example, we are also increasing the counter of the number of weak pointer, of course. Then let's suppose that some of these objects that we have created started to go out of scope, so that they are destroyed. of course, the number of shared pointer is reduced. Every time that we destroyed one of these, it is decreased by 1. And when the number of shared pointer goes to 0, like in this example, also the managed resource is automatically deleted. But as I told you, the resource manager is still alive because the number of weak pointer is different from 0. The resource manager is deleted only when also the number of weak pointer goes to 0. So in this case, also the resource manager is removed. And you don't have any memory leak because everything is controlled by the smart pointer themselves. So any question? I know that it is quite easy, but just to be sure that we can go on. Okay. So now I have some question for you, but before the question, I just want to show you, this is very quickly the list of possible construction, assignment, and move operator that can be used with the smart pointer, with the shared pointer, just to show you that which kind of constructor and assignment operator we were calling in this example. As I told you, this line corresponds to the call to the constructor that takes in input a raw pointer. Then in this case, we are using the copy constructor with the shared pointer that should be this one. Yeah. This is the default constructor. I forgot to add it to the list, but basically it is creating a shared pointer to null pointer so that you don't have the resource manager, you don't have also the allocated resource, of course. In this case, we are using the assignment operator, which is this one. Here we are using the move semantics for the move constructor, which is here. You can see ref. And here we are assigning sp2 to null pointer, which is basically the way you can detach your shared pointer from the managed resource. This is the case, of course, for the constructor assignment for this shared pointer, but then we have also some other methods in the interface that can be used, for example, to access the managed resource. And these two operators are the same that you can find for the raw pointer, of course, the arrow operator and the dereferencing one that gives you the possibility to access the managed resource, so the memory location your pointer is pointing to. But you also have this get method that gives you back the raw pointer. You can check the number of shared pointer that are pointing to the same memory resource using this useCount operation, useCount method. And you have also the overload of the bool operator that basically allows you to do something like this with your shared pointer. We have also other two methods that allows you to basically, again, reset or detach your pointer from the pointed resource, or to change, to redirect, let's say, your shared pointer. This is just a quick overview, because now I want to move to the weak pointer and ask the first question. This is the list of constructor, assignment, and move operator for the weak pointer. If you can just please have a quick look to the list operator of this kind of constructor. I just want to ask you which constructor is missing here. I know that it's a bit boring to look at the list of constructors. It is just a quick question. Sorry? Yes, the default constructor, but there is another one, which is, the question is, the correct question I should ask is, with respect to the shared pointer, which constructor is missing? Sorry, it was an important part of the question. Okay. So with the raw pointer. Basically, if you have a look here, we have this kind of constructor which takes in input the raw pointer, okay, of the same type, but here you don't have the same constructor. It is completely missing, because the point is that you can only create a weak pointer to a given resource, of course, to a given memory allocation, only starting from a shared pointer or using another weak pointer. So using the copy constructor, or using another assignment operator, or maybe another constructor that takes in input a shared pointer, so that you cannot create a new, let's say, you cannot create a weak pointer to a new memory location. You can only create a weak pointer to existing memory location that are already shared by the other shared pointer or weak pointer. moving instead to the observer and modifiers, so to the other methods of the interface of the weak pointer, we have something which is similar to the one of the shared pointer, which is the useCount method that gives you back the number again of shared pointer, which are pointing to the same memory resource, so not the number of weak pointer, but again the number of shared pointer to the same resource. You can check with this method if the weak pointer is still valid or not, which means that basically it returns true when all the shared pointer pointing to a given, of course, memory location have been destroyed, so that basically the resource is no longer here. And it means that basically also the weak pointer is expired, which means that basically it is pointing to null pointer. And then again, we have other two methods that allows you to reset the weak pointer so that it will point to null pointer, or just to swap the resource pointed by two weak pointer. But then here we have another important method, which is the most important here, which is this lock method that gives you the possibility to obtain from a weak pointer a shared pointer. So basically there are two possibilities here. If you have a weak pointer that is expired, which means that you don't have any other shared pointer that is pointing to the same memory resource, if you make a call to this lock method, it will return a shared pointer to null pointer, because the resource is no longer here. So it will provide you a shared pointer to a valid resource, but the resource is not present. So it just gives you back a null pointer, a shared pointer which points to null pointer basically. Instead, if the weak pointer is not expired, which means that there is at least somewhere in your code one shared pointer that is pointing to that resource, it will return a valid shared pointer. And this is an important method that we will use in some of the examples. So here I have another question for you. Assuming that this list of methods from the interface is complex, so I'm not cheating, is the complete one, I'm not cheating, I'm not trying to hide some kind of method. The question is, can you see what is missing from this list of methods with respect, again, to the one of the shared pointer, concerning the accessor and observer? Unfortunately, I didn't split the slide with the two interfaces. It would have been easy, but... So I think that I can... Yes, but there is something more important. So you just look to the observer and modifiers, and let's go back for a while. Yes. Basically, what we are missing are the accessor to the underlying resource. If you have a weak pointer, basically you cannot directly use it to access the pointed resource. Here you don't have this dereferencing operator or the RAll operator. So this is quite interesting, I mean, because basically you have an object that is pointing to something when it is still valid, but you cannot use it to access what it is pointing to. And the other interesting stuff is that with a weak pointer, you cannot even control the lifetime of the resource, because it is only the set of shared pointers that are pointing to the resource that are able to control the lifetime of the resource itself, because it is only when the number of shared pointer goes to 0 that the resource is deleted. If you have, you can also have 100 weak pointer to the same memory resource, but if the number of shared pointer is 0, then the resource is gone. You can only have the resource manager. So the question is, why do we need a weak pointer? Basically, they seem to be quite useless, right? Because as I told you, they don't provide method to access the pointed resource. The only way that you can use them, basically, it seems to be let's say, for the creation of a shared pointer, if the weak pointer is not expired, and they cannot control the lifetime of the managed resource. So they seem to be a bit useless, but actually this is the way they have been designed, because this is the right way to use them, because basically the unique usage of the weak pointer is to check the existence of the managed resource, basically. So they have been built for that purpose. So that basically if you have a weak pointer, you're not in any way influencing the lifetime of the pointed resource, which is good, of course, because if you don't have that allocated memory anymore, you're not forced to keep it alive, because you need a smart pointer to the resource itself. But at the same time, if you have a weak pointer, you can still access the resource if the resource is still alive by creating a shared pointer. So this is exactly the way they should be used, basically. So I have two examples now that I think can be useful to better understand why these weak pointers are useful together with the shared pointer. We start with this first example, which is the circular dependency. I have to give a good explanation, which is not so easy, but in any case, let's suppose that you have a kind of data structure with this kind of link between the objects. We have three objects. You can imagine this like a tree of data or something like that. You have three objects of the same time. You have the object A and the object C have a data member which is a shared pointer to the object of type to the object B. This is our starting point. Let's suppose that now for some reason you need also a pointer from B to A because maybe you want to be able to let's say to access this object using the object B. My question here is which kind of pointer should I use for this link basically? I could use a shared pointer, a raw pointer, or maybe a weak pointer. Let's start with the first case, which is the raw pointer. Let's assume that I put in this object a data member, which is a raw pointer to the object A. Here we have a problem. In this case, what if the object A is destroyed, but the object C is still alive? If the object C is destroyed, basically, since it contains a shared pointer to the object B, and this is the only, and also the object A is destroyed, you don't have the problem because you don't have anymore a shared pointer which is pointing to this resource, which is automatically deleted. But the problem is that if C is still alive, then for sure also B is still alive, because here we have a shared pointer which keeps it alive, okay? Let's suppose that at this point I delete somehow this object A, and I have a raw pointer to A. The problem is that B, after the destruction of this object, B will contain a dangling pointer to A. Okay, this is the Italian. You will have a dangling pointer to A because this object will be destroyed. We will have a raw pointer that is pointing to the destroyed memory allocation, but the problem is that with a raw pointer you are not able to say if this pointer is still valid or not, because it will still contain the originally pointed memory allocation, the address of the pointed object. But the object is no longer here. And the problem is that you're not able to say if the pointer is dangling or not, because you can just see the value of the pointer is the memory address. And of course, if you try to access this object, which is no longer here using the raw pointer, you will have an undefined behavior from your code. The other possibility is to use for this pointer from B to A a shared pointer, but here we have a very interesting case because let's suppose that the C object is not important here. Let's suppose that at some point I try to destroy the object A. A contains a shared pointer to B, so that the destructor of A at some point will try to destroy the shared pointer to B. Since B is only pointed by this shared pointer, because we assume that C is no longer here, the destruction of this shared pointer, which is the unique pointer pointing to B, will also let's say, cause the destruction of the object B, of course, the invocation of the destructor of B. But the problem is that B is containing a shared pointer to A, so that it will try to destroy A, and so you can imagine how things go on at this point. There is a circular dependency, which is basically a kind of endless loop, which will never be resolved during the execution. And basically, you can see from one of the examples that are in the Git repository, you can see that the destructor of the object A and B are never called. Actually, your code is not let's say, blocked by this condition. It continues to the end. But the destructor of these two objects are never called, so that you have a memory leak. So the third possibility, of course, is to use the weak pointer, which is the correct solution for this kind of problem, because basically, if you use a weak pointer instead of a raw pointer, you will be always able to say if this weak pointer is still valid or not, because you can make a call to the expire function of the weak pointer, which tells you if the object the pointed resource is still alive or not. But at the same time, with a weak pointer, you're not able to to control the lifetime of the pointed resource, so that at the point when you will try to destroy the object A, basically you will not have, again, this kind of circular dependency between the destructor that will cause this kind of endless loop, let's say, somehow. So this is a first kind of, I think, a funny example of application of this kind of pointers. I think that I will skip this second part, maybe. No, we have an exercise in this, so I will tell you something also about this. So very quickly, let's suppose that we have this kind of object. It is a generic type. I don't define it in my example, but in our main function, for example, we are using for some reason pointers to this kind of to this type basic. We are not creating directly with new pointers to this object. Instead, we are using this factory function, which is defined here, which takes in input, let's say, a set of parameters that are used for example, in the constructor of the object. It is a very generic condition. And let's suppose that here we are doing some very expensive operation because we need to compute something because the allocation of this object, and maybe something also expensive in the constructor of the object itself. So basically, the problem is here that the constructor of the object is a kind of expensive operation. And what if we need to use in different point of our code this pointer for, let's say, for the same set of input parameters, so that basically in different point of our code we are creating we are doing multiple creation of object for the same type, for the same set of input parameters. So the problem is that we are doing multiple time expensive operation that can be somehow avoided if we are able to store the already created object. And this is the scope of introducing basically a kind of caching mechanism in our factory function, so that basically instead of always calling this factory function with the set of input parameter for the object that we want to create, we can use a cached version of the same factory function, which basically stores the already created object in a cache, which is in this case represented by this unordered map. Okay. So what is the idea of this function? Basically, when you ask for an object, for the creation of an object with a given set of input parameters, okay, in this case, the first operation is, instead of directly creating a new object every time, like in this version, you are first checking if the object corresponding to the set of input parameters for some reason is already available in your cache. So you do this check in this part of the code, because here you are accessing this unordered map for this set of input parameter, so that if the object is already here, this call with this accessor with the square bracket to the cache will provide you a pointer to the already created object. In the other case, it will provide you a null pointer, so that if this is a null pointer, you will enter this if block, you will create a new object, a new pointer to object, you will store this object in the cache, and then you will return the newly created object, so that the next time you call this cached factory function with the same set of input parameter, you will not create another time with this object, because you will just access the corresponding element of your unordered map. So this is a kind of, let's say, of optimization with respect of this original factory function. The problem is related to the usage, of course, of the raw pointer in this case, because the problem is that if we are creating, let's say, the pointer to object for the same set of input parameter in different point of the code, the question is when should we call at the end the delete on the pointer of the object, because you are creating the object for the first time, and you start to use it, and then you call this cached factory function in another point of your code. You are creating let's say you are getting new pointers, let's say, for the same set of parameters that are all pointing to the same memory location, of course, but at some point you will need to delete the object itself, because otherwise you will end at the end of your code, you will have a memory leak. The problem is that with this kind of implementation, you don't know when you have to call this delete, because there could be at least another instance of this object pointing to the same memory resource at some point in your code, but you cannot, you don't know when you have to call this delete. And of course, the other problem is that everything here works if we have null, also if we have a null pointer here at some point for a given set of input parameters, which is the case when we have deleted, let's say, the memory resource because we have decided for some reason that we don't need anymore the object pointing to the given memory resource for a given set of input parameters. So that basically at some point you have to put a null pointer here for a given set, for a given value of int, because all the instances of pointer to object pointing to that resource have been deleted. And the problem is that, of course, you cannot do that because this is just in the scope of the cached factory. So this problem can be solved basically introducing also in this case a weak pointer. So this is just an upgrade of the previous cached factory function using the smart pointer. And the idea here is to create a cache which is still an unordered map, but it is storing the weak pointer to the type object instead of storing the raw pointers. And this function returns a shared pointer instead of returning a raw pointer again. The implementation here, let's say it is the same of the previous case, because when you provide a value for the index for this input parameter, the first operation that is performed is a check on the existing cache, just to see if for some reason the object is already here, so that you are accessing the element corresponding to this value for the index. This can be a null pointer, okay, because if the object is not here, the map will return you a weak pointer, which is let's say an expired weak pointer, so that on this weak pointer you can call lock, and you will obtain a shared pointer, which is a not valid shared pointer that will point to null pointer. The other case is instead when for the value of the input parameter you already have a weak pointer which is not expired, because you have already called this function somewhere in your code for the same input parameter. And in this case, you will get a shared pointer here, which is not a null pointer. It is a valid shared pointer. And in this case, you will skip this if block. In the other case, when you have a null point with a shared pointer that is not valid, you will enter this block. You will create, you will reset the shared pointer so that after this call, it will point to the newly created memory location, and you will put it, let's say you will convert it in a weak pointer, and you will store it in the cache, so that for the next call it will be already available. And the good news for this code is also that the external code, let's say the usage of the external code that is using this cache factory basically doesn't need to take care of the memory release of the provided resource, of the provided shared pointer, and of course also of the cache, of the update of the cache status, because everything is already performed automatically by the weak pointer itself. So basically, with the introduction of shared pointer and the weak pointer that int operates in this case, we are basically solving all the problem that we were discussing for the previous version. So at this point, I have to ask you if you have any question so far, and then. Well, in the original, let's say, agenda, I was thinking that this was the point where we started to solve some problem, but I think that we'll do that at the end of the session. So this is just a reminder, just to tell you that at this point of the presentation, you should be able to try to solve these two exercises that you will find in the GitHub repository. So do you have any questions so far? Okay. Okay, I don't want to spend time by describing the exercise. When you start to do that, maybe I can discuss it with you.
Is the shared pointer thread state? Like now you have in the thread pointer to the same
the only protection, again, in multi-threading environment is for the part of the counters, for the number of shared pointer and number of weak pointer. So that part is an atomic operation, so that it is basically serialized. But for the other part, you can have a race condition if you try to access the same resource, the same pointed memory location from different threads.
But the count is shared across threads.
Yes, and that it is atomic, the operation that updates the counters.
Okay.
Okay, so then when we'll focus on the exercise, maybe I will give you some information about what I am asking you in the exercises. Okay. So as I told you, this smart pointer provides more or less the same interface as the raw pointer, so that you don't have to make big changes in your code if you decide to use them. And this is also true for some specific usage like dynamic polymorphism and casting. You know for sure what dynamic polymorphism is, but I put here as a very quick example. Here we have basically we have this base struct with the virtual f function, and then a derived structure which derives from base with, let's say, a specific implementation of the same method, f. And in my main function, I'm creating a pointer to the type base, making a call to new derived. So, and then here I'm calling the method f from this pointer. And of course, my question here is which implementation of the f method are we calling? You already know that we are calling the version implemented by derived, of course. And this is just a quick example to tell you that you can do exactly the same thing also with the smart pointer, so that if you're using dynamic polymorphism in your code with the raw pointer, you can do that also with the smart pointer without changing anything. I didn't put the example with the shared pointer because I have an exercise also for this. So then I will ask you something about the dynamic polymorphism. And you can do the same operation that you do with the raw pointer also for the casting, because C++ implements some, let's say, some function for the pointer casting which emulates what is normally done with the raw pointer, so that if we have the static cast, dynamic cast, and const cast for the raw pointer, you have basically the same operation also for the smart pointer. It is just a different name. We have static pointer cast, dynamic pointer cast, and const pointer cast, and they make basically the same check at runtime or compile time, like let's say the old version, the version for the raw pointer performs. So that with the static pointer cast, you will have a compile time conversion check. With the dynamic cast, you will have the runtime conversion check. And with this const cast, you can basically remove the const condition from your pointer. So, and also in this case, I don't have an example because I provided just 2 exercises that maybe we can try to do together, but they are very easy, just to ask you to make some quick experiments with the polymorphism and casting with the smart pointers. Okay, so let's move to the last example of smart pointer. So as I told you, there is a third type of smart pointer which implements the semantic of unique ownership, unlike the shared pointer and the weak pointer. So basically, when you have a unique pointer, you can be sure that the instance of unique pointer is the only instance that is pointing to the provided memory location. This is the concept of exclusive ownership semantics. Now I have again the same question for you. If you have a look to the list of constructors and assignment operator of the unique pointer, let's compare this list with if you remember it, with the list for the shared pointer. My question is, can you see what is missing here? Again, this list is complete. I'm not hiding constructors or assignment operators and so on. It is something which is, of course, related to the concept of exclusive ownership, to the fact that you can have only one instance of unique pointer at a given time that is pointing to a given memory location. So the answer is, yeah?
Unique pointer from a unique pointer, obviously.
Yeah. But also, if you have a look, there is something usually here, which is the copy constructor and the assignment operators, which are, of course, are missing because you cannot copy one unique pointer to another unique pointer. You can only move one unique pointer to another one, which is, of course, required by the unique ownership semantics. So yes, what is missing is, of course, the copy constructor and assignment operator, because unique pointer is a so-called move-only object. So you can just move the resource, which is in this case always the pointed memory allocation. You can only move this resource from one pointer instance to another one. You cannot have two unique pointers that are pointing to the same memory location.
So do you have to use std move to do that?
Yeah.
Std move.
It is deleted. This is. I think that is necessary. If you try to do that, you will probably get an error because it is deleted. I have to check. I'm not sure in the example for sure there is this case, but yes, I think so. Maybe you guys, Mauro and Paolo, you have already. I think that you need also in this case, because it is just a deleted copy constructor, but you still have to call std move in this case, for example. Yeah, I think so. Yeah, right. Okay, another interesting difference of the, let's say, between the unique pointer and the other smart pointer is that unique pointer is the only one that is available in two different template specialization. One is the unique pointer to a single object, and the other one is a unique pointer to an array type. This is the only pointer, the only smart pointer that have this kind of template specialization. Basically, it's not true that you cannot do that with the shared pointer, but it is something that you should not do, and then we will have an example about this. And of course, the two different template specialization also provide a different interface method, basically for the accessor operators, because in this case, for the templates for the single object specialization, you will have the dereferencing operator and the arrow operator, like for the smart pointer, while for the unique pointer version specialization for the array type, you have the square bracket accessor, like for an array, for the standard array, basically. There are also some common methods, which are, again, the get method, that returns the raw pointer, and then again, the overloaded bool operator that allows you to check the validity of the raw pointer, basically. So as I told you, there is the possibility of having a unique pointer that is pointing an array and not to a single object, but this kind of specialization basically should not be used. In this case, it means if you need a pointer to an array, basically there are other containers, other objects in the STL that can be used, like vector and arrays and so on. So this version basically should not be used because there are other containers that are better for this kind of situation. So why do we need a unique pointer? The idea of a unique pointer is basically to provide a kind of raw pointer with some additional facilities for the automatic memory management, because they are basically, they don't have an overhead in performance or memory usage with respect to the raw pointer. So they are basically a raw pointer with some additional, let's say, additional facilities that allows you to automatically manage the pointed resource. But otherwise, they are basically the raw pointer. And they are well suited for a return type for a factory function, for example, like in the example before, because in this case, you are providing with the factory function the most flexible type of raw pointer, of smart pointer, because it can be easily transformed, converted, in a shared pointer. But at the same time, you are not forcing the external code that is using your factory function to use a shared pointer, because maybe the unique ownership is enough for the external code. So, but also in this case, we will have an example that will give you some, let's say, some better idea. And basically, we have two examples. One is this exercise that gives you the possibility to, let's say, to make some experiment, some easy experiments with the unique pointer, and you can have also this another exercise that gives you, let's say, it asks you to upgrade the cachefactory function in order to use this unique pointer. And then when there will be the time for the exercise, we will discuss together. So, any question again? No? Okay. So how is the pointed resource deleted by the smart pointers, by the shared pointer and unique pointer? By default, the memory location allocated in the first creation on the heap is destroyed using the delete operation, the standard delete, let's say, when you're using a shared pointer or a unique pointer to a single object T, and it is instead default deleted using the delete with the square bracket if you are using a unique pointer with the template specialization for the array type, of course. This is the default condition. But also these two objects, unique and shared pointer, gives you the possibility to specify a custom delete procedure, basically, so that you can decide what should be performed by the smart pointer when the last instance of shared pointer of the single instance of unique pointer is destroyed, so that you can provide the so-called custom deleter, which is in the form basically of a callable object, which can be provided as an input parameter for the shared pointer case, and the input parameter and template type for the unique pointer. So this is a big difference, since in this case, for the unique pointer, when you provide a custom deleter, basically you're also specifying the type of unique pointer. And the same is not true for the shared pointer, where the custom deleter type is not part of the template parameters. So this is quite important because it makes a big difference in this case, for example. Let's suppose that you have an STL container like a vector which contains smart pointers, which can be unique pointer in one case and the other pointer shared pointer, and you want to use custom deleters for this kind of object. And you want to use different custom deleters for different elements of this vector. So for different instances of unique pointer and different instances of shared pointer, you want to use different type for the custom deleter. Can you do that? If these smart pointer, of course, are stored in an STL container like a vector. JG, I know that you know the answer to my question. Yes, okay. The point is that, of course, if you use here different type for the custom deleter, then you will have different unique pointer type, and as I told you. And instead here we will have, also if you use this different type of the custom deleter, you will have always the same type of object. And the problem with vector, I mean the problem, it is the way it is defined, you can only store a single type within a vector. So basically you will not have, for example, in this case, a vector of unique pointers with different custom deleters type. So another question here, as I told you, the unique pointer is the only smart pointer that provides the support for this kind of template specialization. So for a point, it is the only smart pointer that can point to an array type. But of course, I could do something like this. Just have a quick look. I can define a shared pointer to a point of type double. The constructor of the shared pointer, by definition, expects a raw pointer. And this code will provide, of course, a raw pointer, which is in this case an array. And the compiler is happy with this line, of course, because the definition of the constructor is not violated. Can you see what is the problem here? You can do that in your code. You will create a shared pointer to an array, basically. I don't know if we will have all the time for the exercise, so maybe I can just give you an hint. And the problem is, what is the deleter that is called when we destroy this object?
The one without the square brackets?
No, because it is always using the shared pointer as only the default delete, let's say. So the problem here is that you will have a call to delete while you will need a call to delete with square brackets. So here, this is the problem. You could solve this problem here by providing a custom deleter, which deletes the memory using the delete square. But of course, this is not a good idea, of course, because in that case, you can use the unique pointer But again, also the unique pointer to an array is not a good idea, and you should use other STL containers like vector or array and so on. So this is a question for a bad usage of the smart pointers. Okay, so now I have a list more or less of performance-related consideration and best practices for this kind of object. The first one is about the shared pointer creation. As I told you, when you create a shared pointer, basically you are creating two objects, because you have the resource manager, sorry, you have the managed resource, which is the memory allocated on the heap, and you have the resource manager, which is also allocated on the heap. So basically, when you create a shared pointer for the first time, the first shared pointer to that memory location, you are making two memory allocation with respect to the single memory allocation that you do when you create a raw pointer to a given type. The good news is that the C++11 provides you also a function, which is a make shared function, which gives you back a shared pointer for a given set of input arguments that basically are the input arguments that you have to provide to the constructor of type T. And this make shared function basically performs a single memory allocation. It creates a memory location on the heap big enough to contain both the resource manager and the managed resource, so that you will have one single bigger memory allocation instead of having every time two dynamic allocation. So that basically you can do something like that, like in this example. You're calling this case with the full, let's say, syntax, this shared pointer as P, specifying the type here and here with make shared, and you can also, let's say, better version, let's say, using auto, when you don't have to specify, of course, the returned type, which is given by this make shared function. The bad news here is that with make shared function, you cannot provide a custom deleter. So this function should be used for the creation of shared pointer every time that you can do that, basically. If you don't have to use a custom deleter, you should always use this make shared function. Also because basically if you use make shared, you don't have to call anymore the new operation on your code. So basically you're fully respecting the RAll idiom, which is implemented by the smart pointer. The other issue related to the shared pointer is, of course, that the shared pointer has also twice the size of the raw pointer, because you have two pointers, basically, the pointer to the resource manager and the pointer to the allocated memory on the heap, so that you have always twice the size with respect to a raw pointer. And this is another issue for the shared pointer. Another one is related to basically to the implementation of the resource manager, because it seems to be a quite easy object. You know, you have just the arrow pointer to the memory resource and then two counters. But this is not completely true, because there are some, let's say, inheritance and virtual function invocation which are involved in the usage of this resource manager that can introduce some overhead when you use it. But the good news is that this virtual function machinery is only involved with the final destruction of the resource manager. So basically it only happens one time, let's say, when you use this kind of pointers. The other issue is basically related to the question about the usage of pointers, of smart pointer in multi-threading environment, which is about let's say, the reference counting manipulation, because every time you create a new shared pointer, you destroy the weak pointer, you make a copy, a move, and so on. You need, well, there is an automatic update of course, of the reference counting, so that every time you do that kind of operation on the smart pointer, you will also need to access the resource manager and change the status of the resource manager itself. And also these are atomic operations, so that they are basically critical part of this object if you use them in a multi-threaded code. So basically you introduce a part of serialization in your code. But the good news for shared pointer is that basically it's no more expensive than dereferencing a shared pointer, so it's no more expensive than dereferencing a raw pointer. So basically, if you have a shared pointer, you want to access the pointed memory allocation, that operation is not more expensive than doing the same operation with a raw pointer. So you don't introduce any overhead for this kind of operation. And then some comparison between the different type of smart pointers. shared pointer and weak pointer, as basically they have the same impact on your code for the size in memory point of view, because they both need a resource manager and the located memory, of course. And they also, let's say, introduce the same atomic manipulation operation on the resource manager, because if you destroy a weak pointer or if you destroy a shared pointer, you still have to update the status of the resource manager, and it is basically the same operation on different data member. Talking about a unique pointer instead, as I already told you, basically this object has a 0 overhead with respect to a raw pointer, because in this case, when you create a raw pointer, when you destroy a raw pointer, and so on, basically you are not using a resource manager, because you just have the allocated memory resources. So you're not performing extra operation, let's say, on this object just to keep the consistency of the set of shared pointer and the weak pointer. And so you don't have also the reference counting manipulation. So for this reason, this unique pointer basically has the same performance of the raw pointer, but also it provides you all the, let's say, the automatic management of the pointed resource. Okay, so just to summarize some best practices. So as I told you, smart pointers are, let's say, a good choice if you want to provide pointers in the interface, basically, of your, let's say, if you're developing a library, smart pointers are a good choice for the interface of your library. While raw pointers, basically, if you use them in the internal part of that library or in your code, they are perfectly fine. I mean, as long as you remember that you have to delete the allocated resource, of course. Talking about memory allocation and memory delete, you don't have to create smart pointers from existing raw pointer. This is an important point, of course, because if you have in your code at some point a raw pointer that is created by a call to new, and then you pass this raw pointer to the constructor of the shared pointer, for example, this is perfectly fine from a compiler point of view. It's not an error, but the problem is that at some point that raw pointer in your code can be deleted. And the problem is that then you will have a shared pointer that is pointing to a memory location which is no longer here, but the problem is that the shared pointer is not aware of this condition, because the delete of the memory allocation has been performed outside, let's say, the architecture of the RAll idiom. So this is, of course, a problem. Unique pointer should be used every time you need a raw pointer, basically. If you don't need a shared ownership, in that case you have to use, of course, a shared pointer or weak pointer, but if you need a raw pointer with unique ownership, the unique pointer should be your choice, because as I already told you, basically you don't have any overhead with this kind of smart pointer. So this is the case, for example, of the factory function. I already told you to don't use a shared pointer, a unique pointer for array type, because in this case you can use a vector or an array. So the best choice in that case is not using a smart pointer. As I told you in the previous slides, always use make shared whenever you can instead of new, because in this case you will have a single memory allocation instead of two dynamic memory allocation, and always use weak pointer for a shared pointer that can dangle. So this is related to one of the first examples that we have seen. Again, if you have a pointer that can at some point point into a memory allocation that has been deleted, the weak pointer is a good choice, because in this case you will not introduce any impact on the resource lifetime, and at the same time you will be able to control, let's say, to have a look to the resource, to the pointed resource, so that at this point, using weak pointer, you can create a shared pointer if the resource is already alive, and otherwise you're able to see if the resource is already alive or has been deleted, for example. The last best practice is about the memory occupancy, because as I already told you, basically the allocated memory is released, is deleted when the last instance of shared pointer to that memory location is destroyed. But the problem is that if you have a weak pointer somehow, let's say somewhere in your code, the resource manager will be still alive, because it is deleted only when the last weak pointer is destroyed. So this resource manager, which seems to be in our mental model a small object, can be also quite big, because it also stores the deleters. So if that deleters contains, for some reason, a lot of, for some reason it can contain some data. It can be a quite big object in memory, so that you have always to consider also this point. If you have a weak pointer, it's true that the resource manager can be deleted. Sorry, that the pointed resource can be deleted, but the resource manager is still alive. And if the resource manager is a big object, you're using, let's say, a big, somehow big part of your memory. So this is another point to take into account. This is not really a best practice. It's something that I find very useful every time. It's just to have a look to effective C++ series. It's not marketing that. Okay, I have some other stuff. I think that we have the time. Mauro, do you think that we can go on? There is the disk case, if you want. Yeah, I think that we can do that. No? This is another trick example of usage of the smart pointer that I think can be quite interesting. So let's have a look to this class. I have this class object, which has just a single private data member, which is this integer, can be any type basically, and we have two public methods, one set value, which of course set the values of the m value variable, and then we have a modify method. The implementation of modify method is this one. It takes in input a single value and makes a call to this work on object function. This is not a method of the class, it is, let's say, an external function which is defined here. This function does very stupid stuff because it just makes a call to set value again. It is just to create an example where we have to call an external function, basically. This is more or less a common situation with the visitor pattern. This is not the visitor pattern, but if it is, let's say, inspired by that case. So if you have time, just have a look to this pattern, just to have the real, let's say, definition of this case. In the main function, I'm creating a pointer to this object type, and then I'm making a call to this modify method, which is this one. These modify methods make a call, as I already told you, to work on object function, which is here, and provides that takes in input an integer, which is the value that I want to set, and an instance of pointer to object. And here I'm passing as pointer this pointer that, as you know, is a pointer to the, let's say, to the instance, to the present instance of the object class. Is it clear so far, the description of this example? Because my question here is, what if I change the interface of this work on object so that instead of taking a raw pointer, it expects a shared pointer? So everything else is not changed, basically. I'm still doing the same stuff, but here I'm making a call to work on object, and I should provide an object of type shared pointer and not a raw pointer to object. The problem here is, of course, that you have this modify function that in the old version gives an input to work on object, this raw pointer, but the problem is that this raw pointer it cannot be used in the new version of work on object, because in this case the function expects a shared pointer. So the question here is, what would you do if the interfaces are updated as I've described? The problem is, of course, that you have to decide which shared pointer, how to create a shared pointer here so that you can provide it to the work on object function. Any idea? We have a lot of time, so then we can discuss this beautiful example. No, okay. Sorry? Okay, you don't have to tell anyone else that information. It's just a secret, of course, that the final answer to the example. So, yeah, but the problem is that if you don't know that, how can you do this kind of upgrade in your code? I think that at least this is the first attempt that I will do, and that I have actually done, is just to try to create a shared pointer from this pointer and then pass it to work on object in this way. This is a first possibility, of course, and the compiler is happy with this version, of course. But what's wrong, of course, with this solution, which is not a solution? Yeah, exactly. At the end of this modify function, we'll have the destructor of the object, a shared pointer, which is called, of course, so that the shared pointer is the only instance to this memory location, which is the memory location of this object, this instance of the object that is calling this method, so that basically it's trying to destroy himself. And at the end, you will have an undefined behavior from your code. So this is not a good solution. The correct solution is basically the one that you suggested, which make use of shared from this. And this is how your code must be modified to perform this operation. Can you see what are basically the main differences with respect to the shared pointer case? I will go back. This is the starting point, basically. You have object, work on object here with this pointer, and here you have the raw pointer to object. With the upgraded version, we have this condition. As you can see, there are some important differences. The first one is that your object needs to derive from this class, which is a class that belongs to the standard template library, which is enable shared from this. Yeah. Oh, yes, for sure. But then you will also to provide the answer. So
you've shown the wrong answer, like with the share pointer there. Can I make a share pointer with the empty deleter? If I really want to cheat?
Yeah, I think so. We should try, but I think that this will work.
Yeah, because the empty
Why not?
Leave the things there. It's a very dirty trick. But
yes, but probably is, let's say, smaller than implementing all the derivation from the enable shared from this and all the suggested stuff. So yes, yeah. You can suggest also as a final solution for the implementation in the standard library. Okay, so the first difference, as I was saying, is that you need your object needs to inherit from this enable shared from this. And here is interesting to see that we are using the CRTP pattern. I don't remember if you are ready. Oh, yeah.
More.
Okay, so it's something that you will see tomorrow. Basically, here you are inheriting from this templated class, and you're providing as a template parameter the same type of your class, basically. This is the first difference, so you have to introduce this derivation. Then the second difference that here, instead of manually, let's say, creating the shared pointer, providing to the constructor this pointer, you're making a call to this shared from this, that is basically the same that you've seen in the Boost library. And then the last difference is that in the original the original instance of the pointer in the main function must be a shared pointer. Here you cannot have a raw pointer anymore, because otherwise you will have a kind of exception, a specific exception in this kind of example. So these are the main differences. I will not go too deep in the implementation of this stuff, but basically the idea, just have a look to the first line, is that the enable shared from this object contains a weak pointer, as a data member contains a weak pointer to the same type of your object, basically. So that when you create a shared pointer to your object after the introduction of this inheritance, basically you're creating a shared pointer to your new kind of object, which also contain the weak pointer of this class, of course. And so that finally you will end with a condition like this one. You create a shared pointer to this type T, primed, which just means that it is your original object type plus the part that are obtained through the inheritance. This shared pointer, of course, creates a resource manager and a managed resource, so a dynamic allocation for this kind of type. And here you will have a weak pointer back to the resource manager. And this is what gives you the possibility to make a call of make share in your class here. because here you are creating this shared pointer, making a call to this shared from this method that belongs to the enable shared from this class, and this method creates the shared pointer, basically making a call to the lock method of the weak pointer. And so we will have back a shared pointer to the same resource manager that will avoid basically that double free corruption that will be present instead using the raw pointer. Here I have another interesting exercise that I've tried to do myself, which is having a look, to the implementation, which is really useful. Yeah.
One comment and one question. The comment is that I like this thing because it shows that other example they showed beginning with A, B, and C,
yeah.
the pointers and the
circular dependency.
Dependencies that look like, oh, who cares about this? No battery. So, my question is the new main that you use for the share pointers, do you have to do it, or can you just skip the main with the new statement?
Please, again, can you repeat the question?
If you go back to the previous slide.
Yeah.
Here now the main is different than before.
Yeah.
Before you had the new thing, now you're doing the share pointer.
Yeah.
Is it something you have to do, or?
Yeah. If you try, what you mean is, what if I try to keep this line?
Yeah, keep the same main by using the.
Okay. No.
All the other.
You cannot do that. We will get, in particular, you will get a bad weak pointer exception when you make the call to shared from this.
Okay.
Because basically you have to start with a shared pointer, because basically it is related to the constructor of the shared pointer, which makes a call to a set of functions that creates, because the constructor will make this link between the weak pointer and the resource manager, basically. So I think that I am done with this part. Yeah. So that's it for the smart pointers. Then we will discuss maybe some details with the exercises. The battery is over. So, do you have any question? Yeah.
Can I ask something about the make shared operation, which you mentioned should be preferred? So, as far as I gather, the only difference from the other approaches that you potentially do two allocations in one case versus just one in the other case. Is that it?
Yes, it's that it basically.
So the speed up I might get would only be.
It's only during the allocation. Yeah,
yeah.
The point is just that. Yes, there is also, let's say that could be a drawback actually, which is a minor drawback, but it can be present, which is related to cache invalidation. Because basically, as we said, when you make a call to make shared, you are making just a single memory, bigger, let's say, memory allocation that will contain both the allocated memory for the standard raw pointer and the resource manager itself. The problem is that every time you make a call, of course, to the resource, you make some operation like creating a new shared pointer to the same memory location. You have to make an operation on the resource manager. Basically, you have to increase the number of shared pointer for the same resource. If you make the allocation of the shared pointer with make resource, it can happen that the resource manager and the memory and the allocated memory are on the same cache line. It depends on the size, of course, of the allocated memory, but it can happen. And the problem is that what if we try to use a code like this when we create a single shared pointer with make shared, so we are in the condition that we are discussing. Then here we do something with our object, we are modifying and doing stuff, it doesn't matter, and then we create a new shared pointer here from the same memory location, basically. So here we are upgrading, somehow we are changing the status of the resource manager. Of course, when we do that, basically, if we are on the same cache line, we can invalidate also the data part, let's say, also the raw pointer part. So this is a possible drawback. It is, of course, a minor, because it's not in... Okay, it doesn't matter. because it is not intended that we use that we create and destroy the shared pointer within a for loop or whatever, so that it is we are creating and destroying multiple times this object and upgrade and changing the status of the resource manager. But this can be a drawback. For your question, yeah, the only difference is basically that you're making a single bigger allocation.